All right, it's time for the third section of Chapter 6, which is about square root functions and square root inequalities. So we're going to talk about how to graph square root functions. This is something we touched on a little bit in Algebra 1. So our goals today are to graph and analyze square root functions and then to graph square root inequalities. New vocabulary to be on the lookout for: square root functions, radical functions, and square root inequalities. So as we go through the notes, you should make sure you jot down the definition or make sure you understand what it means when those terms come up. All right, a square root function is a function that has a variable under the square root. So for example, if I have the square root of 2 times x, if I had f of x is equal to that, this would not be a square root function because the variable isn't under the square root. But if I have f of x equals the square root of 2x and the variable is under the square root, then it's called a square root function, which is a kind of radical function. Radical functions are functions that have variables under any kind of radical: square root, cube root, fourth root, fifth root, etc. Today we're focusing on square root functions. So let's take a look at our parent function. The parent function of a square root function is f of x equals the square root of x. The graph looks like this. It starts at 0, 0, because when I plug in 0, I get 0. I cannot plug in negative numbers because then I would get imaginary numbers, and I can't graph those on the xy axis because the xy axis represents real numbers. So I have to plug in something greater than or equal to 0. So this would be my domain of the parent function. The range is also greater than or equal to 0 at this point, because if I look at the y-axis, I start at 0 and I go up forever, but I don't go down. My intercepts are 0, 0. That 1 point, this 1.00, is the x-intercept and the y-intercept. It's not defined where x is negative, and if we look at our end behavior, this end behavior is a little different because this end right here, first of all, it doesn't go on forever, but as x gets close to 0, y gets close to 0, so it's zooming in on that point 0, 0. But then on the other end, it looks like the end behavior we've talked about before. As x goes to positive infinity, so as x gets really positive, y gets really positive. Not as fast as a polynomial function does, but it will continue to grow forever and ever in the positive direction. So let's take a look at how the parent function can help us identify the domain and range of any square root function. So if I take a look at this function, f of x equals the square root of x minus 2. Thinking back to what we know about transformations of functions, when I subtract something inside my parent function, in this case under the square root, I know that this is going to move my graph to the right 2 units, because it's minus 2. Remember, when it's inside the function, it's opposite of what you think. So when I subtract 2, it moves it to the right 2. So remember that my domain can only include values that keeps what's under the radical non-negative, meaning it can be 0 or positive. So I asked myself, okay, what's under the radical? Well, x minus 2. So I can only have values for which x minus 2 is greater than or equal to 0. It can't be negative. When I solve that, I get x has to be greater than or equal to 2, so that's my domain. And if I take a look at what happens at 2, if I plug in 2, because that's the smallest domain value I have, f of 2 is 0, so my range has to be greater than or equal to 0. If I were to graph this, and we'll look at this in just a second, but my graph would start at the point 2, 0 and go to the right like this. So it looks like my parent graph just shifted to the right 2 units. So the domain, x is greater than or equal to 2, range, y is greater than or equal to 0. Okay, you guys try this one. All right, your answer here should be C. And there's the work for how to get that. This is how we get the domain, where we set what's under the square root equal to 0. And this is where we get the range, where we plug that kind of end point of the domain into our function. Okay, we talked a little bit about this, but transformations of square root functions. This is just like what we talked about back in Chapter 2. It's very similar to what we talked about in quadratics in Chapter 4. So whatever is underneath the square root, so whatever I add or subtract to x under the square root, moves it horizontally left and right. So if I have x minus this number, whatever h is, moves it right. And if I end up with h being negative, so it would look like x plus 2, just like in this last one we looked at here, it was x plus 4 under the square root, but it moved it to the left 4. Just like we talked about before. K, which is outside of the square root, that's my vertical translation. If k is positive, it moves it up, and if k is negative, it moves it down that many units. And a, the number that we multiply in front, gives me the orientation in the shape. So if a is less than 0, meaning if a is negative, then it flips or reflects over the x-axis. And then, ignoring the negative, if a is greater than 1, then I get stretched vertically, so it gets taller. And if a is between 0 and 1, so if it's a fraction bigger than 0 but less than 1, again, notice we're looking absolute value, so ignoring the negative, then it gets compressed vertically, so it gets shorter. Okay, so let's take a look at this. Thinking about the rules that we just talked about, this negative 4 under the square root is going to move it to the right 4 units. The plus 2 outside of the square root is going to move it up 2 units. And this 3 multiplied outside is going to be a vertical stretch by 3. So it's going to get 3 times taller than the parent function would be. Okay, so these left and right translations to the right 4 and up 2, that gives us our minimum point, or kind of like the starting point of our function. So that point hk is where we're going to start our table of values. We'll start our table of values at x equals 4. We're going to have the same shape, I said again, as the parent graph, but it's going to be stretched vertically. So let's take a look at what that would look like. So again, because of my h and k, I'm going to start my table of values at x equals 4, and I get 2 for y. Plug in a few more values so that I can get the right shape of my graph. And this is what my graph would look like. I graph the 0.42, the 0.55, the 0.6, 6.2, and so on. Notice that the end behavior as x gets really positive, y gets really positive. So f of x goes to positive infinity as x goes to infinity. My domain here, x is greater than or equal to 4 because it starts at 4 and goes to the right. My range, y is greater than or equal to 2. Okay, let's take a look at this one. Again, before you even start graphing, you should analyze the translations. A plus 5 under the square root means move to the left 5 units. A negative 6 outside of the square root means it's going to go down 6 units. And this negative 1 out in front, since it's a 1, it's not going to stretch it or compress it, but the negative is going to reflect my function over the x-axis. Okay, so we already have an idea that my graph is going to look something like this, and that this point is going to be negative 5, negative 6, to the left 5 and down 6, which is what they tell us here. This is going to be my point where I start. I'm going to make my table of values starting at x is negative 5 and see what it looks like. So when I make my table of values, notice I start here at negative 5, and here they're just plugging in some numbers above that. Notice they're choosing x values that give them integer values of y. You don't necessarily have to do that. You can estimate some of the decimal values, but sometimes it's nice to spread the x values out a little bit so you get a better shape. And this is what my graph would look like. Here's my starting point at negative 5, negative 6, and here I'm graphing my different points. Notice that the end behavior, as x goes to positive infinity, y is going to negative infinity. So my domain this time is x is greater than or equal to negative 5, because it starts here at negative 5 and all my x values are to the right. And my range is y is less than or equal to negative 6, because I start at negative 6 and the rest of the graph is below that. So I want you guys to try these next 2 examples. Start by graphing this one. Okay, your answer here should be D. Notice that this should have been moved to the right 2 and down 3. And this graph here shows us that. And then it has a vertical stretch of 3, and we can see that in this graph as well. And then find the domain and range of this graph. All right, this function has a domain of x is greater than or equal to negative 1. My starting point here is going to be negative 1, negative 4, move to the left 1 and down 4. And all of my x values are going to be larger than negative 1. and my range will be less than or equal to -4 because of this negative. The negative means the shape of my graph is going to be like this. This is the point -1, -4. So my range is going to be below -1. I'm sorry, -4. Y is less than or equal to -4. All right, we are going to skip example 3 and move on to example 4, which is square root inequalities. Be very careful. Anytime you're graphing an inequality, you always have to think, is it going to be dotted or solid? And you have to think about shading. No one should have to remind you when I see a function or something with x and y, but it's an inequality instead of actually being a function. I have to think about those two things. Is it dotted or solid, and where do I shade? So first of all, here they're graphing y equals 3x plus 5, but notice that they're graphing it dotted because it's greater than, not greater than or equal to. And here's how you would go about graphing that. You set what is under the square root greater than or equal to 0 to get your starting point, which in this case is x is greater than or equal to -5/3. Then notice I set up a table of values. I end up getting irrational numbers, so here I just rounded them to the nearest tenth. Notice I started going with -1, 0, and 1, and then I skipped ahead to 4. That helps you get, again, a little bit more variety of points that you can graph. And then we graph the boundary, but the boundary is a dashed line because it's greater than, not greater than or equal to. Okay, so my domain is x is greater than or equal to -5/3. Because y is greater than, I'm actually going to end up shading above the boundary, but I have to only shade greater than or equal to -5/3 as well. So just like we did before, to make sure you shade in the right place, we're going to test a point. Here we're going to test 0, 0 because it's not on the boundary. So is 0, because remember my original inequality is y is greater than the square root of the quantity 3x plus 5. So I test 0, 0, and it gives me something that's false. So I'm not going to shade underneath where 0, 0 is. I'm going to shade above. Notice that they only shaded up to -5/3 on the x because x cannot be less than -5/3. So I can only go up to here, and it's all the points above. So any point in this region going up infinitely would make this inequality true. Okay, so you guys try this one. All right, your answer here should be D. And here is the work for how you can find your starting point at -2. It's greater than, not greater than or equal to, so it's going to be dotted. And then again, we end up shading above here after you test a point. Okay, this is not on your note guide, but we're going to take the last 2 minutes just to look real quick at the word problem from example 3, which is a physics problem actually. It says when an object is spinning in a circular path that has a radius of 2 meters with a velocity, which we're representing with v in meters per second, the centripetal acceleration, A, in meters per second squared, is directed toward the center of the circle. The velocity v and the acceleration A of the object are related by this square root function. V equals the square root of 2 times the acceleration. So we're going to graph the function in the domain A is greater than or equal to 0, because that's the only thing A could be. Plus, logically, acceleration well, actually, acceleration can be in the negative direction, but for right now, they're telling us to graph it where acceleration is positive or 0. Okay, so here's my function. We make a table of values starting at 0. That's where they told us to start. So this looks a lot like the parent function. That 2 just stretches it a little bit. And these, notice again, they're having to round the v values in this case. Here, A is like my x and v is like my y. So they're having to round a little bit because you get a bunch of irrational numbers when you deal with square roots, but you go ahead and graph that, and that's what the function looks like. And then it says, what would the centripetal acceleration, which remember that is represented with the variable a, of an object spinning along a circular path with a velocity of 4 meters per second be? So we need to solve for a. We can tell from the graph, it looks like it would be about 8. But we are going to check our estimate by plugging in. So I plug in 4 for the velocity. I square both sides. And I get 16 equals 2a and 8 equals a. So the acceleration looks to be 8 meters per second squared. We got those units from the original problem. All right, I'll see you in class to practice.